Okay, so let's begin. And I think that everybody here has heard of the terms of the entangled state, right? For a long time, because entangled state is very popular now, especially in the quantum information science and technologies. And for studying the concept of the entangled state, I think it's better for us to learn another concept that is called the tensor product state first. So today we'll learn the concept of the tensor product state. So the tensor product is a very frequently used item in the quantum mechanics. And so what is the origin of the tensor product? Because we have many opportunities to face the problems of the multi-particle systems. And for the multi-particle system, we need to have the tensor product. And sometimes we have only one particle, but we have several observables. For example, we have the angular momentum. We have the orbital angular momentum for the particle, and also have the spin angular momentum for the particle. So we also need to have the tensor product for that case. And also sometimes we have the same observable. For example, we have the position or the momentum, but the position or the momentum has three components. And for each component, we have the eigenvector, eigenstate of that. So we also need to have the tensor product state, the concept of that. So that's why we need to have the tensor product for so many places. So the tensor product comes from these cases for the multi-freedom. So what's the meaning of the multi-freedom? What's the meaning of the freedom here? The freedom comes from such several cases. The first, that we have the first is the multi-particle or the multi-partite system. We have the particle 1, particle 2, right? Particle 3. And also, for each particle, we have eigenstate for that. The eigenstate for particle 1, eigenstate for particle 2, and so we need to have the tensor product. And also we have another case for the multi-freedom, that is the single particle, but with multi-observable. For example, for the particle, only one particle, but the particle has this. This is the orbital angular momentum, right? And also we have the spin angular momentum. And so for the angular momentum, we have the eigenstate for the orbital and also for the spin, right? We have this. This is the eigenstate of this observable. And also we have the SMS, that is also the eigenstate for this observable. And now we have two states, and so we need to have the tensor product of that. And also we have the case for the single particle with the same observable, but with multi-components. For example, we have the X P, right? And for X and P, we have the X, we have the Y, we have the Z, which are the eigenstates for the different components of the position operators. And also for P, we have Px, Py, and Pz, and which are the eigenstate for each component of the momentum observable, right? So it should be noted that with the different components, but these components are commutable or commuting. So we do not give you the example of the Lx, Ly, and Lz, right? Because Lx and Ly are not commuting. Ly and Lz are not commuting, but X and Y, X and Z, Px and Py, Px and Pz are commuting. Okay? So we have the several cases for this multi-freedom. The freedom could be the particle, could be the observable, could be the different components of the observable. And for all of these cases, we need to have the concept of the tensor product. This thing is needed. Here, okay, that is a very beginning, very preliminary introduction of the origin of the tensor product. Because after we have studied the concept of tensor product, we can go to the concept of the entangled state. Before tensor product state, we cannot go to the entangled state, okay? So the tensor product is very, very important. And in many previous lectures, books, and so on, the tensor product is also called the direct product in many books or reference literatures. But we prefer to use the item of tensor product instead of the direct product, because direct product is a little bit confusing, because in mathematics, direct product has very tight connection with the direct sum for the subspace we have learned before, especially in mathematics. And so we prefer to use the tensor product item here. So now, this is a very, very beginning for that's the origin of the tensor product. Okay, and now next we'll see what is the definition of the tensor product. The definition is quite simple. We can define the tensor product like this. Suppose that we have a vector psi1 belong to this subspace that is H1, and psi2, or we prefer to use another letter. Okay, phi2 belong to this, another subspace. We have this is a subspace H1 and this the subspace H2. And from this, we can define a Hilbert space, which is equal to H1 tensor product H2. Like this. That is psi1. I would like to ask you to pay more attention of the notation here. We have the psi, that is the label of the state, and 1 outside of this ket means the different freedom. So 1 and 2 outside of this cat notation means the freedom 1, freedom 2. It could be the particle 1, particle 2, or the observable 1, observable 2, or the component 1, component 2. Anyway, it means the different freedom. The different freedom is labeled here outside of the cat. Okay, that's a convention. We should be very careful because today we should be very careful about the notations 1, 2, and 3 because we also have the 1 and 2 inside of the cat. If inside of the cat, that means for this label, maybe we have several cats, we have several vectors, okay? So here, the 1 and 2 here outside of the cat means it is the label of the freedom. Particle, observable, or the component. Okay? Got it? Okay. So psi 1 tensor phi 2. And this is a new vector. Belong to what? Belong to this. So H1, H2 are the subspaces. H1 and H2 are the subspaces. And H is the tensor product state of H1 and H2. And the vectors in this space is denoted like this. Psi 1 tensor phi 2, 1 and 2 outside of the cat. Okay? Okay, so that is just the definition for the tensor product. And next, let's see. We have some properties. Of tensor product. A tensor product. The first property is the commutativity. Commutativity, that means that the tensor product can be commutable to each other. The psi 1, phi 2 is equal to the phi 2, psi 1, like this. Psi 1 tensor phi 2 is equal to phi 2 tensor psi 1. So this is a very good property because it is commuting. 1 and 2 are commuting, so it's very good. The second property is that the linearity of this operation, and that is if we have psi 1 tensor phi 2 like this is equal to a psi 1 tensor phi 2 and also equal to psi 1 tensor a phi 2. That's it. So that is the linearity. So if you have some psi a, psi 1, or b, phi 2 or something, that's the same. You can use these regulations to have some generalization of the linearities for this. Okay? And third one property is the distributivity. Distributivity. And this is also one of the properties of the linearities. For example, if we have the A psi 1 plus B, well, this is for the first freedom, psi 1, 1, and psi 2, 1. So that is the first freedom. But for the first freedom, we have two vectors. That is vector 1 and vector 2. Okay? If this vector tensor the psi 2, what's the result? The result is that is equal to A psi 1 1 tensor phi 2 plus the b psi 2 1 tensor phi 2. And this is one of the distributivity. And also we have the psi 1 tensor. If the phi 2, we have two choices. Maybe we have the 1 phi 1 2 plus b phi 2 2. And the result is similar to that one. That is the a psi 1 tensor phi 1 2 plus b psi 1 tensor phi 2 2. So you should be very careful for this, for the subscript here. I have emphasized that the subscript outside of the cat means the different freedom, right? And the subscript inside of the cat means that for the same freedom, you have several vectors. Okay? Got my point? Okay, good. So we can give you an example. We can give you an example of that. Oh. The examples now. If we let ui 1, you can find that this is a basis, right? Basis. In the subspace H1, we have the basis. That's for the freedom 1. But for the freedom 1, you have several choices of the basis. The I could be 1, 2, 3, 4, 7, something like that. Okay? And I is equal to 1, 2, n1. So that means for the first subspace, the dimension is n1. Okay? That's a n1 dimensional subspace. And it is denoted by the basis of the EI1. You have n1 choices of the basis for the freedom 1. And also you have another that is VJ2. That is another basis for, it belongs to the subspace H2. And J is equal to 1, 2, and N2. That we have two subspace, and we have two different bases for that. The subspace 1. That is n1 dimensional. And subspace 2, we have the n2 dimension. And so, what is the dimension of the whole space spanned by the tensor product of H1 tensor H2? The dimension for H is equal to the dimension of H1 tensor H2, and it is the dimension of H1 and dimension of the H2. That's so it's equal to n1 times n2. So you can find that dimensionality for the tensor product is quite different from the direct sum, because the dimensions for the direct sum is the summation of all of the dimensions of the subspaces. But it's a very interesting thing that because if you have two systems, you have two particle systems, and for each particle systems you have a two. If you are to have the two-dimensional, you have the two-dimension of the freedom. For example, you have one particle 1 that is a 1/2 spin system, and a particle 2 that is also the half spin system. So if you have this, the summation of the 2 plus 2, that is equal to 4. And 2 times 2 is also equal to 4. So it is, in many cases, it's very easy to be confused about the direct sum and the tensor product. So now you should be very careful about this concept, distinctions between the direct sum and the tensor product. Okay? Okay, so these are some very, very fundamental. And for such two subspace like this, we have the two bases. So, and the psi 1 could be expand using the basis of the UI1, right? So that is Ci UI1. So you find that the basis in the freedom 1 and this vector is in the freedom 1. Okay? And you have another phi 2 can be spanned by the basis for the subspace 2. Okay. From this, what can you get? What can you get? You can have operation of the tensor product of the psi 1 and phi 2. And let's calculate. And I can calculate here, and you can calculate yourself. Okay? Let's try. The psi 1 tensor phi 2. What's that? It's equal to Ci tensor like this. And according to the rules here, what can you get? You can have Cidj so that's the result. If you have if you have the arbitrary vectors in H, which is spanned by the tensor product of H1 and H2, any vectors can be written like this. So you can use the tensor-based product of the two bases to expand the any vectors like this. Okay? And this is the coefficient. And Cidj is the coefficient for the expansions of any vectors in this tensor product state. Okay? Okay. So we call this state, let's say it is called the phi. This state has a name. It has a name. The name is, that is called the tensor product state. The name is of this state is the tensor product state. That means the state is represented by the tensor product of the two states. But entangled state is not. Entangled state can never be represented by a tensor product state. We'll see it later. So now we should have the first concept, that is a tensor product state. The tensor product state can be written like this. It is a tensor product of the two states, or several states. You can have the tensor product of the psi 1, tensor phi 2, or tensor kappa 3 or something, you can have too many tensor products of several vectors, state vectors. That's the tensor product. This is one of the very simple, most simple case for the states. But we have many other cases. That is the state which cannot be represented by the tensor product state. So the tensor product state is like this. We have many tensor product state cases in our quantum mechanics, because in quantum mechanics at the undergraduate level, you have learned the two-particle system, that is two-spin-half system, right? You have learned that. You have two particle maybe. For each particle, it has the spin is 1/2. And then you have 4 states for that. Remember that? You have the singlet and the triplet. Singlet is only 1 state. And the triplet, you have 3 states. But among the 4 states, you have only two tensor product states in the triplet. But the singlet state and one of the triplet states are not the tensor product states. Remember that? If you do not remember, go back to review the undergraduate level quantum mechanics, and then you get what I mean. Okay. Okay, we can write a very simple example of that. For example, for psi 1, phi 2, like this. If we only have, psi 1, we have only 2 bases. For example, that is the C1, U1, 1 plus C2, U2, that is also 1. The 1 outside here means the first, the freedom one, okay? And the phi 2 in the D1, V1 for the 2 freedom, and D2, that is for the second freedom and the second basis for that. So you can calculate what is the result of the tensor product. You will get psi 1 tensor phi 2 is what? It's equal to C1 D1 U1 1, like this. C2 D1 U2 1 and so you have 4 terms. You have 4 terms altogether for this tensor product, right? That's a very simple case for the tensor product for the 2 freedoms. And for each freedom, you have 2 bases. And that's the result. You have the 4 terms, like this. Okay. Right. After that, we can write down another vector state, the state vector. And let's see if the 2 vectors are the same. Let's see that. If now we have chi something is equal to like this. Actually, this expression is the same as this one. That means the Aij equals to the Cidj, right? Okay, so any vectors belong to the tensor product space is like this. it can be represented by this. So we can have such an example. If chi is equal to something like this, like this, what will happen? What will happen? If now we have such a vector, it's possible because from the expression of these vectors in this space, Aij can take any values, provided that Aij it belongs to the complex number. It could be the complex number, it could be the real number, it could be any number. It could be non-zero numbers or the zero, right? So you can have this state. If you have such a state, let's see what will happen. So this thing is phi, right? If phi equals to chi, then let's see that. We can get the C1 D1 is equal to this, and also equal to C2 D2, right? And also we have the C1 D2 is equal to 0, which is also equal to C2 D1. So we can have such the relations for the C1, C2, D1, D2. You can find that C1 times D1 equal to the C2 times D2 with equal to 1 square root of 2, right? And C1 D2 and C2 D1 is equal to 0. So it's what? It's a very strong contradictions, because for this you must have C1 or D2 or C2 or D1, one of that should be equal to 0. But provided that you have one of that equal to 0, you can never have this, the above expressions for that, right? So what? So phi and chi cannot be equal to each other. So that means chi is a state which cannot be represented by what? The tensor product. So this state cannot be a tensor product state. This state cannot be a tensor product state. And for this state, which cannot be represented by the tensor product state, what's the name of that? It is called the entangled state. Entangled state, at the very beginning, it is defined like this. The entangled state is a state which cannot be represented by a tensor product state. That is a very original definition for the entangled state. But nowadays, it is too simple, because quantum entanglement is very complicated. But at the very beginning, for very original definition for the entangled state is defined just like this. Yeah. The entangled state is a state which cannot be represented by a tensor product state. But it could be represented by the summation or superposition of the two tensor product states. I have this tensor here, right? And normally very many people like to just ignore this cross-cycle notation is complicated. So, but anyway, if you like, you can do that. You can just ignore this, but it means the tensor product state, or the direct product. For the very long time ago, the people prefer to use the items of the direct product. Direct product here, we must pay more attention. That just means, it doesn't mean the direct product in mathematics. It means the direct product of the physics. That means the tensor product. The tensor product is just the definition. It's over there. Okay, so these are just some basics of the tensor product state and also the entangled state. So I would like to give you some more remarks of the entangled state, because we have seen that is called the chi, and also we have several cases for the chi. We can have the 1 over square root of 2, and that is u1, v1, right? And also we can have u. We can have not only the plus here, we can also have the minus. That is also the entangled state. And also, we have this, something like this. u1, 1. v2, 2. u1, 2. And v1. Also, we have 4 choices. We have 4 choices. All this are the very preliminary or just very simple examples of the entangled state. That is to the 2-partite entangled state. That is called the bare state or bare basis. That is the most simple example of the most simple case for the entangled state. In many places, the people would like to say, oh, we have the bare basis or bare state or something for the 2-photon entanglement, 2 ion, 2 atom entanglement or something. You have learned many times of these items of the bare state and bare basis. And that is the most simple or the most preliminary, that's very simple case for the entangled state. Okay. And from that introduction, we have known that the entangled state cannot be represented by the tensor product state. That is some very simple definitions for that. However, the entanglement or entangled state is a very complicated concept nowadays. We can have more than 2 freedoms in entangled state. We have multi-partite, multi-particle systems, and then we can have the n-particle entanglement. And for the n-particle entanglement, we have several cases, not only like this. For the n-particle, for example, particle system, we have the W state. That is also called the Vienna state. For the full freedom, you have only 1 and 2, 1 and 2. You have very simple choice. But for the n-particle, you have many choices for the permutations or different particles to have the entangle like this or like that. So you have the W state, that is the entangled state for the n-particles. And also you have the GHZ state. That is also for the n-particle, also for the n-particle systems. So for the n-particle system, you can have many types of the entangled state. You cannot say for sure what is what. And also you have the known state. The W state is a resource for the quantum computing. If you are studying the quantum computing or quantum computation or something, or quantum simulation, you prefer to study the case for the W state. And GHZ state is a very fragile entangled state. For the N particle, GHZ state entanglement, if some entanglement is broken, then all of the entanglement of N particles will be broken. But for the W state, if you have the N particle entanglement first, and then you break one of the entanglement, and then you will lose one entanglement, then you left the N-1 entanglement. So W state is stronger, is very robust, and GHZ state is fragile. Once the entanglement for the GHZ state is broken, all of the entanglement for the N particle entanglement will be broken either. Okay, like this. And known state is an entangled state that is very frequently used in quantum imaging. Actually, that is N particle, 0 particle, that is known state. Right? You have 0 particle, that is a vacuum state. And another one is the N particle, you have the entanglement for that. So that is the N0 plus 0N. It's very similar to that one, but one of the state is N particle, another one is the 0 particle, and then you plus a 0 particle, N particle of that. So known state is frequently used in quantum imaging at the very beginning for the entanglement-based quantum imaging. So this state, W state, is used in quantum computing. GHZ state can also be used for the quantum computing, but W state is a pursuit because it's robust, and the GHZ state is very fragile. And also for all of the state, we can adopt the 2 particle or more particle, multi-particle entanglement to realize what? To realize the quantum key distribution. Because we have many protocols for the quantum key distribution, such as we have the BB84 that is based on the single photon protocol, but also we have the ERCOT 91 protocol that is based on entanglement, based on the entangled state of the photons. And for that, you need to have the, that is not the WGHZ, you just use the bare state. You can realize the QKD based on the ERCOT 91 protocol, that is entanglement-based QKD. And for this known state, that is quantum imaging, for the quantum imaging, at the very beginning, if you use the entangled photons to realize the quantum imaging, you use the known state. But nowadays, for the application for realization of the quantum imaging, we prefer to not to use the entangled state. We prefer to use maybe a thermal state or pseudo-thermal state, because that is much more simple to be realized than entangled state. Entanglement, remember that entanglement is very fragile. It's very hard to generate the entanglement first. It's very hard to realize, to generate the entanglement. And the second is that it's even harder, it's tougher to maintain the entanglement. It's very, very hard to generate, and it's more difficult to maintain. So entanglement is very fragile. You should be very careful to keep the entanglement. And the entanglement is connected with the coherence. Once you have the coherence, it's possible for you to realize the entanglement. But if you lose the coherence, if you have some mechanism for the decoherence, you will have the disentanglement. Decoherence will lead to the disentanglement, definitely. But once you have the coherence, it's not for sure that you can have the entanglement. But if you lose the coherence, the entanglement will be lost, definitely. So we have the theory for the entanglement sudden death. it's dying so quickly, it's just sudden death. It is not like the spontaneous summation, you know that, but the decay is like exponential decay. It's slowly decay, and then the coherence is getting smaller and smaller. But the entanglement, that very quickly, it's sudden death. But also it's possible for the coherence, for the entanglement, to rebirth suddenly also. It's just like in quantum optics, you have the phenomenon of the collapse of the system, and also you have the revival of these systems. And for the entanglement, you also have the entanglement sudden death, or after some period, you have rebirth of the entanglement. So that's some very frontier research topics of that. So entangled state and quantum entanglement are very sophisticated and very important concept in quantum mechanics and quantum technologies. And it has been realized by so many people that quantum entanglement is the most fundamental distinctions with the classical mechanics. So in classical mechanics, we don't have any entanglement. But in recent years, maybe in recent 10 years, the recent 1 decade or something, more and more people are beginning to study the concept of the classical entanglement. And one of the pioneer guys is my supervisor, Professor Joe Abley. He's studying the classical entanglement. And the publication is very hard, but eventually it was published about the classical entanglement. If you like, you can just Google or something, you can try to find the papers about the classical entanglement. Okay, and there are so many complicated entangled states for the multi-part systems, for the atoms, photons, ions, and so on. And also we have mentioned about the double state, non-state, and GHZ state, and so on. So that's something, information about the entanglement. And nowadays for the pure state and for the two-level system or two-state system, the entanglement problems has been overcome. So problems of the entanglement is okay for the pure state. But for the mixed state, for the mixed state, especially for the continuous variable cases, the entanglement has not yet been well defined. So the study of quantum entanglement for the mixed state, especially for the continuous variable case, is still to be explored. So we have a lot of open questions about that. And I would like to give you some more calculation rules about the tensor product later, maybe in next class. We will mention something about the inner product of the tensor product. If you have a tensor product state and not a tensor product state, you can have an inner product. And what's the result of that? I will study that topic later, okay? Okay, inner product for the tensor product state. Inner product for the tensor product state. So you have two tensor product state. Maybe you have the psi psi 1 freedom, the first vector in the first freedom, and you have this. You have this is a tensor product, right? And also you have this. You have two tensor product, and this two tensor product can have the inner product of that. You can have psi 2, 1, phi 2, 2. So that is the BRA. That's a tensor product BRA state. vector, right? And this of this. You have the 2 vector. This is a vector, and this is a cat, and this is a bra. And then you have the inner product of that. How to do that? How to do that? This is a bra and this is a cat. It's quite simple. For the tensor product state, it's quite simple. You just inner product the same freedom first, and then you just multiply to each other, and that's it. So that's for the first freedom, and this is the inner product for the first freedom. And you got it. So that's the definition also for the inner product for the 2 tensor product state. Okay, got it? That's a rule. That's a definition for the inner product for the 2 tensor product state. Okay, the reason, no reason. That's a definition for that. Okay. And so we can check. Now we have the UI, for example, that's for the freedom 1 belong to the subspace 1, and Vj belong to the subspace 2. So you can check the tensor product state by using the inner product for UI1 tensor Vj2. So this is a bra, right? That's a bra for the basis of the tensor product. And you can have the UL1 tensor VK2. So that is the basis, the tensor product of 2 bases, and you got the cat. And this is the basis, tensor product of the 2 bases for the bra. So you got the tensor product, the bra, tensor product, the cat. And then that's the inner product of the bra and cat. And the result is UI, UL, that's for the freedom 1, and Vj, Vk, that is for the freedom 2. Okay, so what can you get? Because for the freedom 1, for the basis, you have the orthonormal properties for the basis, right? So that's equals to the third IL. And for the second freedom, you also have the similar orthonormal property. So you have the JK. So you have 2 Kronecker delta multiplication, right? And that's the tensor product state, inner product for tensor product state of that for the basis like this. Okay? You got the rule? Okay. So that is the orthonormality for the tensor product state. And I would like to I think it's very important for us to study another thing, that is the operators on the tensor product state. We have studied the tensor product state, and for the next we'll study the operators which can operate on the tensor product state. Okay? Operator on the tensor product. So after study of the state, next one is operator. It's very natural. And suppose that we have the operator A1, which operate on the subspace H1, and B2 operates only on the subspace of H2. We have many these kinds of examples. I will give you examples later about what is A1 belong to the subspace H1, and what is B2 belongs to the subspace H2. We can generalize the A1 and B2 to ask A1 to operate on the tensor product state for H1 tensor H2. So for the H is equal to H1 tensor H2, we can generalize A1 as what? As A1 tensor identity 2. And so this operator, the new operator, can operate on H. Originally, H1 only acts on this. But here, the A1 tensor identity 2 will be able to act on this tensor product state. And similarly, we can generalize B2 to the B1 identity 1, B2. Let's see what will happen. What will happen? For example, we have a space psi 1 tensor phi 2. So this is a tensor product. And now we have this. Like this. It's A1 tensor identity 2 psi 1 phi 2. How to operate? This operate this, and this operate this. You got the A1 act on psi 1, and this is a vector, right? And this vector will tensor the later one. And what's the result of this? A keep invariant. So that is A1 act on psi 1 tensor phi 2. So that means A1 will not act on phi 2 because A1 only operate on the freedom 1. It has nothing to do with the second freedom. Okay? So that's also the case for the B. You can have, similarly, you can have the B2 act on the same state, that is the tensor product state, that is the B2 1 tensor B2 psi 1 phi 2, right? Similarly, this act on this, and this act on this. Okay? So you got the 1 psi 1, this is a vector, and tensors another vector, that is B2 phi 2. And the result is very simple, that is psi 1 and we have mentioned that the tensor product can commute, right? The tensor product of this and this can commute the position. So that is equal to the B2 psi 2. So that means the B2 only operate on the freedom 2, phi 2. It has nothing to do with the first freedom. So that's why you have used many times of this before you study the tensor product state, right? You have several, maybe you have several angular momentum, and you have the J1 only act on the L1, J1 M1. It has nothing to do with the J2 M2. And that's why. But you don't know the reason for that. But today you should know the reason for why you can do that. Okay? I can give you more examples of I can give you more examples of the freedom of we can have the particle 1 and 2. That's too trivial. So I would like to give you another 2 examples. Maybe one is that, what is P? We know that we have the P square, right? Over 2m. So that is the kinetic energy, which is equal to the Px square plus Py square plus Pz square, like this. And what is the eigenstate for each? We have the Px is Px, right? We have this, and also Py is equal to Py. But pay more attention that here, this is an operator, and this is a C number. This is the eigenvalue. So it has no hat. And you have the hat here. Okay? So this is the operator, and this is the eigenvalue. Keep in mind, that's very important. And also your Py is equal to Py. And also your Pz so what's that? So what is P? Actually, this kinetic energy is equal to what? It's equal to this tensor right? So this is a subspace for the Px. This is the subspace for the Py, and this is the subspace for the Pz. And so, plus tensor Py square So actually, you have 3 subspaces. The 3 subspaces, Px belong to maybe X, and this belong to Hy, and this belong to Hz, and the H is equal to Hx tensor Hy and Hz. It's like this. Okay? And then when you define such an operator's kinetic energy here, you can find that for that tensor product space, so that is P, it's equal to Px tensor Py tensor Pz. Actually, it is like this. But normally, we just write P like this. And it is equal to Px, Py, or Pz. That's the same thing. or maybe sometimes you like to ignore this symbol, you can write down like this. If you like, no problem. That means just the tensor product state for these three eigenstates. Okay, so that you have, when you learn the quantum mechanics, you have used the p vector state for many times. You have the x state or p state or something many times, but you don't really understand what it means. And so, similarly, we have the x, and this is the eigenstate for the x operators, right? It is equal to x tensor y tensor z. Sometimes we can write down like this. Okay. Okay. Good. So that's one of the examples of that. So that means the same for the same particle. Same particle. We have only one particle. But for each particle, it has momentum. That's only one observable, right? But it has three components for the momentum. So it has three subspaces. You can have the tensor product for the three subspaces, and you got the whole Hilbert space. You got my point? So that's what I have told you. That's the first example. And the second example is like this. We can have L and S. So we have two observables. Right? For L, we have the L square and LZ, which are the CSAO for that, they are because L square and LZ are commuting. So they have the same simultaneous eigenstate. And for the S, that's similarly, we have the S square and SZ. And for the L square, you have the quantum number of the small l. And for LZ, you have the ML, right? You have the small m sub l. And similarly, for the spin, you have the small s. And for the SZ, you have the ms. So actually for this, so the first freedom 1 is LZ, right? And freedom 2 is the S square SZ. For this freedom, you have the ML. And for this second freedom, you have the SMS. So you have L, ML, tensor, S, MS. And normally you can just write down like the L, S, ML, MS, like this. So we have learned in quantum mechanics in undergraduate level, many times you have the L, S, ML, MS like this. Maybe you have J1, J2, and M1, M2 or something, right? For the same particle, but two different observable. And for each observable, we have the eigenstates. And altogether, we have a total Hilbert space. That is the tensor product space for the eigenstate for both observable. That's the eigenstates. That's the tensor product of the two eigenstates. And so that belongs to this. So this we can say belongs to L, and this belongs to HS. So the H is equal to HL, HS. So that is the tensor product state of that. Okay, you got the point of that? Okay, and Next, we can say something more about the angular momentum, because in angular momentum, it is a very good example for studying the concept of the direct sum, right? What is for the direct sum? In which case we need to have the direct sum? When we have several eigenvalues, and for each eigenvalue we have several eigenstates, right? For each eigenvalue you have a subspace. A different eigenvalue corresponds to different subspaces. And then altogether you need to have the direct sum for the different subspaces corresponding to the different eigenvalues. So that's it. So, for example, if we have this, so what is dimension of that? What is the dimension of this? What is dimension? Tell me. What is dimension of this? Do you know? What is dimension of this? Dimension of HL equal to what? Depends on L, right? It's equal to 2L plus 1, right? Okay, because for the same L, you have 2L plus 1 different eigenstates. So the dimensionality for this state is 2L plus 1. Dimension is 2L. So that is the dimension is equal to the degeneracy of these corresponding eigenstates. Remember? Yes. And what is the dimension of this? That's 2s plus 1. So it equal to 2 if you have the s is equal to 1/2. So if you have only one electron, that is a one spin half system. And so the 2s plus 1 is equal to 2. So that is the 2 state. Okay, if you have more electrons, maybe the s could be the 0 s. It could be 1 if you have 2 electrons. 1 electron means s is only equal to 1/2. But for the 2 spin, you can have several choices. You have 2 choices. One is S1 minus 1 S2. Another one is S1 plus S2, right? So you have the 1/2 minus 1/2. That is one case. That's equal to 0. Another one is 1/2 plus 1/2. That equals to 1. So you have S equal to 0 and S equal to 1, 2 cases. And for the S equal to 0, 2S plus 1 is equal to 1. All right? But for S equals to 1, that is 2S plus 1 equals to 3. Okay, good. So because dimension of this subspace is 2L plus 1, and this is 2S plus 1. 2s plus 1. So the dimension should be the 2l plus 1 times 2s plus 1. So that is dimension for the tensor product space. Okay, you got the points? And let's compare some comparison of tensor product and direct sum. Okay, the tensor product and direct sum. I think that the dimensionality is a very good specification for that. We know that for the tensor product, that is dim H1 times the dim H2, right? So that is what we have emphasized many times. But for the direct sum, the dimension H1 plus dimension of H2. So the dimension the dimensionality for the direct sum is the summation of the dimensions of the two subspace. And for the tensor product, the dimension is the dimensions multiplication of the two subspaces. Okay, so that's one of the differences. And for the direct sum, for the physical origin is what? I think that it's quite different, right? The subspace, normally we talk about the direct sum that comes from the same, only one freedom. For example, we have only one freedom. We have only one observable, for example. That is L squared. That's the angular momentum for that, right? The angular momentum. So for angular momentum, because you have the L, M, that is one of the subspace, right? This is the basis for the subspace for that. It belongs to the H what? L. And the dimension of HL is equal to 2L plus 1, because that is the degeneracy equals to the dimensions of the subspace. Okay, so altogether, the dimension of the whole space is equal to the dimension of this, right? So actually, that's equal to this, 2L plus 1, L. The L could have the upper limit sometimes, but it does not have the upper limit in some cases. For the bounded state, for example, if you have a hydrogen atom in a bounded state, and you have some confinement of L, which is due to the principal quantum number. So L should be equal to 0, 1, 2, 3, up to n minus 1. N is the principal quantum number. But if the hydrogen atom is not in the bounded state, because after, when you have enough energy and then the atom becomes a free atom, free particle, you will not have that bond, right? Because the energy of this atom will become positive. Because for the bounded state, the energy is negative. From negative to zero, the zero energy is the critical point for the bounded state and unbounded state, right? When the hydrogen atoms become so active, excited, and then it becomes from the unbounded state to the unbounded state, and energy from negative energy to the positive energy, and then it becomes no bond. And so for the hydrogen atom, for the bounded state, the L is equal to 0, 1, up to n minus 1. But for the unbounded state, for the free atom, the L is equal to no bound. For the bounded state, it has bound. But for the unbounded state, it has no bound. And for the positive energy, the energy is continuous. Right? For the bounded state, energy is negative and it's discrete. It's not continuous. But after zero energy, the energy becomes a continuous spectrum. And then no bound for the L. Like this. Okay, well, here, and for the tensor product, that is, you have 2L. Maybe you have 2L, or you have L and S. L and S. So that is the dimension of L is you have that. The first one is Lm belong to HL and SM S belong to this HS. So dimension of that. So the dimension of this is equal to the 2L plus 1 2S plus 1. So that is for the direct, that is for the tensor product state. So that's okay. So the physical origin for the tensor product and for the direct sum is quite different. Direct sum means you have the same observable but different eigenvalue. For each eigenvalue, you have a subspace. You have the direct summation. The direct sum is the summation of the different subspaces. That all of the subspaces belong to the same observable with different eigenvalue. Right? Some eigenvalue is non-degenerate. For example, if the L is equal to 0 or S equal to 0, that is one eigenvalue, one eigenstate. So that is non-degenerate. But for L, which is not equal to 0, or S not equal to 0, you will have the 2L plus 1 or 2S plus 1. So you have the dimensions more than one subspaces for that. So for the direct sum, it's like this. And for the tensor product, you have the two different observables, or you have the same observable with the two different components, or you have the two particles. And so that is our distinctions between of the physical origins for the different the tensor product and direct sum for that. Okay. Okay, we have several minutes. We can have a starting for the representations, quantum mechanics. Representation in quantum mechanics. Representation in Chinese is like this. Representation. And now I would like to give you a very general method for you to study the quantum mechanics, because we have mentioned so many times about the vectors and operators and so on. And but that is just like the geometry. You have some abstract vector, but you do not have any reference. You do not have any reference systems, coordinate systems. Once you have the coordinate systems, you have the analytical geometry, right? Before the analytical geometry, you have the only the geometry, that is Euclidean geometry. When you are in high school or something, you have learned the geometry without the coordinate systems. And after you have the Cartesian coordinate systems, you have the analytical geometry. And so what is representation? Representation is just like the analytical geometry. You have a coordinate system, and then you have from the abstract vectors, and then you have some very vector with the very clear, very explicit component of that, because you have the coordinate systems. Okay? It's just like that. So the representation means, if we say the x representation, the position representation or momentum representation or something, that just means that we use the basis of this. So basis, representation only means the basis. Basis, and this basis, the basis is the eigenstates of some observable. Eigenstates, eigenstate, eigenvector, right, of the observable. So we have so many observables. We have the position observable, right? We have the momentum observable. We have the Hamiltonian observable. We have the angular momentum observable, and so on. So for each observable, you have the eigenstates. And when you use the eigenstates of that observable, that means you use the representation of that observable. So that means if you use this, and this is the eigenstates of the x, right? For example, you may also use the eigenstates of the momentum like this. So this is the eigenstates for the x, for the position observable. So when you use this eigenstates as the basis for the expansion of your vectors, that means you are using the x representation. So it's quite simple. And if you use this eigenstate, the eigenstates of p, of the momentum, that means you are using the momentum representation or the p representation. That's it. So that's the meaning of the representation. And we know that for any eigenstates, they have the three properties, that is normalized, orthogonal, and complete, right? Remember, for all of the eigenstates of the observable, they must be the basis. That basis means that they have three properties. One is orthogonal. Their bases are orthogonal to each other. And they are normalized. The length of that basis of that vector is unity, is 1. That means it is the basis, unit vector, okay? And it is complete. That means the bases are complete, are enough for you to span the whole space, okay? So I think that's the same for the quantum mechanics and for the geometry. They're completely the same. So we have three properties for the basis. And the basis must be the eigenstate for some observable. And we have two cases. One is the discrete case. Discrete means that the eigenvalue is discrete, that is countable, and that is discrete. It could be finite or could be infinite, but even it is infinite, it must be countable, right? That is a mathematical Hilbert space. So for the discrete case, you have the psi n, psi m equal to delta nm. So this thing is called the normal, also orthogonal and normalized, that altogether, that is also normality, okay? Also, that is half orthogonal, and another thing is normal, that is half, and that is the property. So also normality. That means it is orthogonal and normalized property, also normality. Okay, so when n is equal to m, that means it is normalized. When n is not equal to m, that means that is orthogonal. Okay? And the completeness is the resolution of the identity. That means your bases are sufficient. We call this as the resolution of identity, or that's a completeness conditions for the basis. So for any kinds of basis, Once it is called the basis, they have the three properties: orthogonal, normalized, and complete. Okay, so any kind of a basis. And that's the case one, that is for the discrete case. And also we have the continuous. The continuous case in like this. Because I have mentioned, we have emphasized that the Hilbert space for the physics is quite different from the mathematics, because for the mathematics, the discrete case is all. But for the physics, we have expand the Hilbert space to a much larger space, because we have allowed the continuous case for that. The A prime is equal to the Dirac delta function. So this is also the orthonormality. That is the orthonormality for the continuous case. And also we have the completeness condition, or the resolution of identity for the continuous version is like this, is the A is equal to 1. And the integral can be taken for all of the values that it is valid, and you can take that. So for example, if the A is x, the x can be, the value of x can be taken from minus infinity to the positive infinity. And for the one-dimensional for that, and also for three-dimensional, you have three integrals of that. So this is for the completeness, or the resolution of identity for that. So now we have the Hilbert space for the physics. And the Hilbert space for the physics has been much more enlarged than the mathematical Hilbert space, because we have the delta function. We have the Dirac delta function. And when the Hilbert space comes to this world, there is no delta function. And no mathematician regards the delta function as a function. So this condition cannot be included in the Hilbert space in a mathematical version. But for the physics, especially for today, we are using both the discrete case and for the continuous case. We have the chronic delta, orthonormality, and also we have the delta function, orthonormality. We have this summation of the resolution identity, and also we have this integral of the resolution of identity for the continuous version of that. Okay? So that's some very basic things about. And next we can have in some certain representation, you can have the wave function, and also you can have the matrix. So you can have in some certain representation, you can create the wave mechanics and matrix mechanics. You know that the wave mechanics is created, is invented by Schrödinger, right? And matrix mechanics is invented by Heisenberg. So they were invented separately by the two persons. But now it can be unified to be in the same version, that is Dirac version, because we have Dirac notation, so we have the cat and bra. Okay, so for example, we have the side like this. We have this is a vector, and we can, because, right? For any vector, you can write it down like this. So you can have and this expression is like this, Cn. So we can say that the Cn is a wave function. But this wave function is not like the wave function for the in the continuous version. This is a discrete. And also, we can use the dx For example, like this. Psi x, x. And here, psi x is the wave function. So for the same vector, you can have the different version of the wave functions. It could be the continuous, it could be the discrete, and whatever. For any operator, you can write down like this, right? For the operator, it is equal to the identity multiply A multiply identity. So for the discrete case, you can have the and so it is equal to so this, it could be like the matrix element. This is the NM. And also, you can use the continuous version also. You can have the dx and dy. And then you have the x, y, and x and y, of course. And this axy is equal to the broad x, a, and y. So this is not really a matrix element, but it's like the matrix element. And here, if you can expand it in using the discrete basis, you can, of course, you can have the matrix. And next lecture, we'll mention about something about some operators, some certain representation. And also we'll mention about a very important operation that is called the adjoint, or the Hermitian conjugate. Because so many people think that Hermitian conjugate means transpose and then you have the complex conjugate. Yes, you are partially right, but not completely. Because you cannot always write any operator into a matrix. For the discrete case, you can write down the operator as a matrix. But for some other operators which cannot be represented by a matrix, it's a case that very frequently happens. Because, for example, you have the P, the momentum that is minus IH bar partial x, that is continuous. How can you write down the momentum as the matrix? You cannot do that. So that's a continuous version of that. So I think that it's very important for us to learn and to learn the definition of the adjoint or the Hermitian conjugate by heart from the definition from the very beginning, not the transpose and then complex conjugate. Is too simple. It's just a special case for that, okay? So that's all for today, and it's over. Yeah. Okay?